Su, on behalf of Bob Abdouan, who is the person that invited him and his friend since a long time. The title of Professor Su keynote is Combinatorial Fusion, Ranking and Scoring for Computational Learning and Modeling. Professor Su is from Fordham University, New York. He is a Clavius Distinguished Professor of Science and Professor of Computer and Information Science at Fordham University, New York. Was visiting faculty scholar at Keio University as IBM Chair Professor and JAIST as Komatsu Chair Professor, Tokyo and Kanazawa in Japan, MIT, Cambridge, Taiwan University, Taipei, Taiwan, and University of Paris Sud and CNRS, Paris, France. His research interests include combinatorics and graph theory, network interconnection and communications, combinatorial fusion and information geometry, and computational learning and modeling, including machine learning and artificial intelligence. He published 40 books of book chapters, edited, co-edited, 27 special issues in conference proceedings, and over 200 papers in journal and conferences. He served as on many editorial boards of prestigious journals. He received his bachelor from Cheng Kung University, Taiwan, his master from Texas, El Paso, and the PhD from the University of Michigan. He is a senior member of IEEE. Please, Professor Su, the floor is yours.
Okay. Okay, thank you very much, Professor Perry, for the introduction. And I'm very glad to be here to talk to many friends and colleagues around the world, especially the topic about combinatorial fusion, ranking and scoring for computational learning and modeling. And this topic is also very closely related to the conference. Our conference is called International Conference on Computational Science and Applications. So it's really timely and also very closely related to all this. And I'm glad to be able to report some of the recent results recently. Okay, so.
We cannot see her, sorry.
Okay, now can you see the PowerPoint now?
Okay.
Yeah. So, okay, so I have a email address here. So if anybody is interested in getting a copy of the PowerPoint, please let me know. But just to tell you that, my email address is hsu@fordham.edu. It's very simple. Okay. Okay. So by doing that, I'll talk about this.
Left and right.
Couldn't do it. Hold on. Okay, so I divided this talk into 4 parts. Number one is I give one example, very simple example on figure skating judgment. And then I go to combinatorial fusion algorithms. I explain what is that, what is that for, and what is really what's the technology over there. And then, I go to talk about some applications of the, for the combinatorial, learning and also, also machine learning and so on. And then part D there, then I give some discussion and extensions to some information geometry.
Right.
Okay, so we have examples here from science, technology, society, and cyberspace there. And there are many, many examples in many, many different areas, talking about ranking and scoring, okay? And, and let me just go through this very briefly because, we all know this already. Number one on the left-hand side is really crossing the street. This is a picture taken on the Fifth Avenue of New York City. And when you want to cross the street, we look at the left-hand side and right-hand side to see if any cars coming or not. If there's no car coming, we use our ear to listen to see if we hear anything. So if we don't see anything, if we don't hear anything, and in a sense that's safe to go. Well, that's the New Yorkers do that, but not New Yorkers, you don't do that. You look at the traffic light. If the traffic light is green, you can go. If it's red, you cannot go. But anyway, so that's one of the situations there. In our brain there, we are trying to make a decision there, and we're combining audio and visual informations together, and then we get a decision there. The one on the far right hand side is a jury decision there, making process, and that I probably don't want to don't spend time there. You know that in any case there, it's a civil case or the criminal case there. The jurors at the end they have to make a decision there, and it will be a combination of that, and that's something called majority voting or whatever. The one in the middle there is very interesting. It's called active research in chemical space there. And this one is related to chemoinformatics and also, related to bioinformatics also. And here we have one example on that. On the left-hand side here, we have internet search. Of course, everybody knows that. And then on the right-hand side there, we have figure skating judgment. And we're going to get, one typical example there. And then we have something called intrusion detection, and that's in cybersecurity. On the right-hand side is the smart cities. Right now, people are trying to build smart cities so that it will be interconnected and also very secure and also very sustainable. And then on the left-hand side, right below there, we have talking about equity ranking and portfolio management there. How to buy stocks and, how to buy mutual funds and other things like that. And then on the right-hand side below there, we have something called recommender systems. And, we are all very, very familiar with it, okay? Okay, so now come to this something called figure skating. And I just want to give you, I'm not trying to insult you, but this is a very, very simple examples of figure skating judgment. So if we look at the table on the left-hand side, on the right-hand side, so we have 8 skaters there, D1, D2, up to D sub 8 skaters there. And we have 3 judges, J1, J2, J3. So on the left-hand side there, 3 judges give, 3 scores there. 3 judges give, 3 score functions there. And those 3 score functions are really, we look at that, of course, it's really judges assign score to a skater there. And we call that a score function there, okay? So a score function is from the D, capital D is the data set items, to the scores, okay? And on the right-hand side there, we converted each score function there to a rank function there. For instance, in J1 there, we have J1 there give D sub 8 10 points, and therefore D sub 8 for J1, the rank number is 1. And the D sub 4, you got a 6.4 points, 6.4 points, That's the lowest score there, and that's why that is ranked number 8. Okay, so we got from the 3 score functions on the left-hand side, we converted to the 3 rank functions on the right-hand side. Now, on the left-hand side there, we have a score combination there. So we just take the average combination, and then, you can divide by 3 or not, it doesn't matter. Then we sort this score function, that's the score combination that, the 1, 2, 3, 4, the first column there, the score combination there, we sorted that into descending order, then we get a final ranking there. So the final ranking on the left-hand side, after score combination, is 4, 3, 7, 8, 2, 1, 6, 5. Okay. But on the right-hand side there, we have the rank combination there. Now that's the first column there. And we sort this array into, increasing order in the sense that, that means, ascending order. And then, that means that the rank combination, that number is the smaller, the better. And therefore, the final ranking we get is 4.5, 7, 6, 8, 3, 2, 4.1, 4.5, and 1. And here is rank number 4 and number 5, you have a tie ranking there, you have a tie score there. And that's why we use that as a 4.5 and 4.5 there, okay? So this page of the score functions and rank functions and score combinations and rank combinations is very simple, but it tells a lot of stories there. Not only stories there, a lot of theory there, a lot of practical information there. And we get information, this is where we get information there, okay? So I like all of us to take a look at this, okay? We have 8 skaters by 3 judges. Left-hand side is using the scores, and the right-hand side is we convert the scores to ranks. So left-hand side is the score combination, and the final ranking is the final ranking by score combination. Right-hand side, the final ranking is by rank combination, okay? I also want to point out that from the score function to rank function is almost free. And, but unfortunately, and also, very, very interestingly, there are many, many machine learning, machine learning, AI, many results there, or even books don't talk about ranking at all. And this is very, very peculiar, okay? So I like audience of this, conference. We are all experts in computational sciences and, and applications. We like to, one of the messages I'd like to get to everybody is that, well, when we have a score, we score something, it's always free to convert that score to a rank, okay? And then, in the sense that, in the year 2005, there's a paper by Xu and Taksa. We show that under certain conditions there, the rank combination can be better than score combination, okay? Okay, good. So then the next one is that we normalize the score. And here, just by very simple thing, we normalize the score to a linear normalization. So that's the right-hand side there, to the linear normalization, and that's from 0 to 1. So you can see here, D sub 8, it's got a very high score, 10. So we normalize to 1. And D sub 7, in this case, this is a different example. These numbers here are different from the previous page there. So 9.3 is the lowest one, so you get 0 there, okay? Anyway, so this means that linear normalization. And then this is something, I want to show everybody is that we calculate this function called a rank score function here. And that's from the rank to the score there. So then J1 is also from the rank to score, and the rank is what, from 1 to 8. And so J1, we have a function. J2, we have a function. And at J3, we have a function. Okay. And then we draw the rank score function graphs there. And okay, sorry, this is just a vacation wise. It's not COVID-19. I mean, just got some cold. So the right hand side here, the rank score function graph, it shows that J3 is quite different from J1 and J2. Okay, and you can see here. So what does that mean there? Well, here this graph is is a very, very interesting and also very crucial graph here. It shows that J3, well, give very high scores to the rank number 1 to 7, but give the rank 8 very, very low scores, almost 0 in this case, because we normalize the scores to 0, 1 there. Well, what does that mean here? If we go back to that, okay, well, that means that J3 manipulates the score, okay, because J3 here give D sub 8. You see, J1, J2 give D sub 8, 10 points. But J3 doesn't agree with that. So give D sub 8, 5.1. We give everybody else 9.2 and above. Okay, so this is one of the things to catch the outliers, to catch the bias, to catch intrusion detections, to catch the hackers, to catch many, many things. So this rank score function graph is able to do that. Okay, so that's something I want to convey to all us. It's very, very convenient to draw that rank score function graph. And so this rank score function graph was defined in 2002 in this paper here. Okay, so because of that, then we can calculate the similarity or diversity between scoring systems A and B. So everybody agreed that, everybody also very familiar with that. In statistical, learning and modeling there, we use statistical correlations. And over there, we have a score function, we have a rank function. And for the score correlations, we use Pearson's correlation. But for the rank, we use the Cantor-Stars-Spellman rank correlation. But in the computational diversity, computational science case there, in the machine learning and AI, of course, we have ensemble methods. We are combining multiple classified systems. We are combining multiple neural networks. We are combining multiple machine learning AI systems or algorithms. And over there, we have we define. If you see the book, many books there, like Konchava's book about combining multiple classified systems. Also you have to define diversity and so on. Okay, and so here comes to what is combinatorial fusion. Okay, so all the fusion here. So we are talking about we have A is a scoring system and B is a scoring system. So here we just follow the figure skating thing. So we have a score function A, we have a rank function A, we have a score function B, we have a rank function B. We label the data set items as D1, D2, okay? And you can see that then if we add up SA and SB, that's called score combination. If we add up RA and RB, that's called rank combination. If we have score combination, we get a C. We have a rank combination, we get a D. Okay. And this is the general framework of this. And I'm sure this, everybody is very familiar with this. you have a data set coming in. We have attributes, criteria, cues, dimensions, features, indicators, charges, parameters. You can create another, a set of 20 terminologies here. Then we use algorithms or models, classifiers, charges, machine learning, ANN, hypothesis, and cognitive systems and other AI systems. And we try to combine them or try to, of course, from the beginning, you have a, extract the features or attribute. And now you try to combine, select them and then combine them. And then at the end over there, we have algorithm combinations there. And sometimes we call that model fusion also. So this is the general framework to do combinatorial fusion. And this is just some of the details there. Basically we have a D, capital D, is a set of all the data items. R is a set of real numbers. So from D to R is a score function. And then from D to N is a rank function. So the rank score function I defined just a while ago. And also that was defined in the year 2002 in a DIMACS report there. It's from N to R, okay? And, I show you that rank score function already. And then here you can draw the rank score function graph there. You can see that, F sub A, F sub B, F sub C. And you can see that, F sub A, that means the A scoring systems, the algorithm or the model or whatever, right now people are talking about, CNN, convolutional neural network and so on. It's really a rank to score is very, very, linearly related to each other. But the scoring system C is more, you get more higher scores from the beginning and then goes down there. But algorithm B or model B give lower scores, to the higher ranking there, and then it goes down, it decreases down there gradually, and then to zero there. Okay. So this rank score function graph there is something very, very interesting, and also, this is one of the main items of my today's talk there. What I mean by that is that this is a new paradigm of trying to characterize the algorithms or the models and so on. Okay, and then this is related to other things, and we know that in the statistical data correlations we have all kinds of correlations there. We have Pearson's correlation, Kendall-Style, Spearman-Role. We have many other things like Kolmogorov Smirnov test and KL divergence. I'm sure all of us are familiar with all this. But then part B here is the computational information diversity there. And there are many diversities being defined. Q statistics, KW, variance, generalized diversity, there are many other things. But the cognitive diversity I defined here, is between two rank score functions there. And that's very, very interesting. That's the below there, that picture there. Okay, so the cognitive diversity is really the outer loop there. It's between rank score function A and rank score function B there. Okay, so that's one of the the two items there. One is a rank score function, and one is cognitive diversity. And I want to emphasize that at the end of the talk, I also emphasize that rank score function and cognitive diversity are data set or data independent there. You can see here, because rank score function is from N to R, it doesn't go through that D there. And you can see that the score function, for instance, like a Pearson's correlation, it depends on the score function, and the score function is from D to R. And that's why it's data dependent. Okay. Okay, so you can see that this is quite a contrast between statistical data correlation and computational information diversity. And here I define something called ranks of function and cognitive diversity. So, it'd be very, very useful and also very easy to compute. Okay. Okay, now here I just want to give a quick applications of the combinatorial fusion here. And I use those 5 examples there. And, some of the examples, you can see that I have references here. So each one I got a references there and a reference in the back of this PowerPoint there. So anybody, please, if you're interested in looking at this, send me email. I can send you the references there, very quickly. And so number 1 example is in biomedicine, bioinformatics actually. Number 2, sorry, there's a misprint here. It's no vertical screening. It's called virtual screening. I forgot to correct that. Okay, number 2 is virtual screening and drug discovery. And number 3 is in wireless network selection. Number 4 is in corporate revenue forecasting. And number 5 is in cognitive neuroscience. And there are many other applications also. Here I just don't have room and time to go over other applications. Okay, so the first application here is about combining multiple chip-seq peak detection using combinatorial fusion. And the chip-seq, as everybody knows, that is about immunoprecipitation and about how do the DNA sequencers and how do you sequence the DNA and also how to align that with with the original the alignment there, and then there's a difficulty there to find the peak there. So we use combinatorial fusion to overcome that difficulty there. Okay, and this is the result there. We got an average precision for the intersection of two methods there. And you can see that the single cases there, A, B, C, D, E, F there, those are the performance there. And then the combination of 2 cases there, you can see that many of them improve the result there. We are using the combinatorial fusion to do that. Okay. Okay. The second example, that's what they call virtual screening and drug discovery there. And here, and it's this example of the virtual screening and drug discovery using structure-based protein now, and we are using the 5 rank score function there over there, and that means those functions are all scoring systems related to some of the protein and the ligand darkened algorithms there. And that's a rank score function there, about with respect to TK. TK is one kind of protein. And on the right-hand side, that's a result over there. You can see that we have A, B, C, D, E. And then on the right-hand side there of that, we have 2 combinations, 3 combinations, 4 combinations, 5 combinations. And the blue one is a rank combination. The red one is score combination. You can see that the blue one, some of them, they perform much higher in the score combination there. And this paper was published in 2005 there. And that's the result of this. And this paper is published, as I say, we published this paper with Professor Yang of, I think he is right now the dean of, College of Science there at the National Jiao Tong University in Taiwan. And this is about, X coordinate is the ratio between the performance low and higher. And Y coordinate is the ratio between the rank and the score there. You can see that the circle there is a combination, is performed better than individual ones. And X is that it's not performed better than that. So you can see that if we have a higher ratio of the performance, and also the higher ratio of the rank score sense diversity in the same sense, then we tend to be able to improve the result there. So I think this is pretty much in line with what we all know. We all know that if you want to combine two things or a few things or a few experts together, the combination can be better than the individual ones, only if those experts' individual systems are relatively good enough. Because if they're not good, then combination doesn't help. So they are relatively very good enough, and also they are diverse. Okay, and that y-axis is the diversity there. So this picture kind of typify whatever we're talking about machine learning, AI, and other things. That's the expected result there. Okay. Okay, and then this example is about the wireless network selection. When we carry a cell phone, and when we go to in a different area there, we have to the cell phone. We have an algorithm to select the network there because you go to a different area there, you may have a different networks there. Okay, and we use the combinatorial fusion to do that. Okay. Okay, the next example is about corporate revenue forecasting. And, I just want to, go over this very quickly. And, normally in a corporate environment there, we have four managers or four divisions there, EGSC, and then they all give a prediction. And then how do we combine those together? Okay. And, and that's the way we use the score function, the rank function, and then we have a score combination, rank combination, and you can see that improvement by by that combination there, it's by the score combination there is about 5%. By rank combination, we can improve 10% there, and this is pretty much also people at IBM are really doing something like this also. Okay, this one example here I'm talking about. This is cognitive neuroscience, and I just want to explain that what's going on here. So here we have, on the screen there at a computer, you are shown a subject was shown two faces there, left and right, and then the subject will look at those two faces, after maybe 10 seconds or so, and the subject will say, left face is more attractive or right face is more attractive. And then the subject's the movement or the location of the eye movement was recorded, and we, as a sequence there. So that's a sequence of location and the duration there, and location and duration there. Okay, so that the location is XY coordinate, and duration is each point there. And then we are given the sequence there, and we want to predict or forecast. We're going to predict that. Okay, in this sequence, the subject is going to make it left-hand side is more attractive or right-hand side is more attractive. Okay. So we created 5 attributes, and one of the attributes I want to emphasize a little bit is that attribute A is called last duration there. And this paper, this work is collaborated with Professor Shimojo of California Institute of Technology there. And what we do here is that, Shimojo published a paper about 10, 15 years ago. And he and his colleagues showed that the last duration of the subject looking at that left face or right face is very important also. That kind of decided, the subject is going to decide left face or right face is more attractive. Okay. And anyway, so this is the rank score function of all those 5 attributes there. And then, those are combination now. You can see here, I just want to point out to everybody here, attribute A is 90% and the precision at 100. Attribute D is 51%. Okay. But combination of attribute A and but But below here, combination of attribute A and D, it can get to 98%. So that's phenomenal. Yeah. Okay. And that's very, very interesting now. Okay, so here we come to the discussion and the extension now. Number one there, model fusion, combination of multiple machine learning AI models, algorithms. And we had one result after this, it's by 10. We show that combinatorial fusion here can be shown to be used very high throughput perovskite synthesis with model fusion there, and that's in material science there. And then the second item here is multi-layer combinatorial fusion and deep reversal learning. We can show that we done that on the K-many rank space. That means that allow tie rankings there. One of the reasons there in machine learning and AI, people don't talk about ranking that much. Less it's because when there's a tie ranking there, they don't know how to deal with it. Okay, so here we know how to deal with it, because K-many in 1959 and 1962, he pointed out something which we can do. More lately, Hurley, Dr. Hurley and I, we actually show that the K-many rank space is a Hilbert space there, so it's a vector space. Okay. So C of A using the RSC function, and the cognitive diversity. Again, this I just repeat. This is what I just told you a while ago. It's a new paradigm for multiple regression, prediction, and decision making in statistical learning and modeling, ensemble method and model fusion. The RSC function of a scoring system is analogous to combinatorial distribution function, but it's data simple invariant. Cognitive diversity is very similar to the correlation and diversity in computation, but cognitive diversity is domain independent. Okay, the information architecture here, we all know that, if we have a, ranking of 3 elements there, 1, 2, 3, then you have a, hexagon there. If we have a ranking of 4 elements there, then we have the, B sub 4 and, B and C there. And those 2 pictures are really the same one, the same graph there, but, taken it differently. Because the second one, B says that the B sub 4 is a combination of many B sub 3s. Yeah. Okay, so this is all without ties, but if there's a tie ranking there, this is what happened here. If we have a hexagon, we have 3 elements there. The permutation, we have 6 points there. But if we have a tie ranking there, if we have 2 ties, then we have all the points on the edges there. If we have 3 ties, then we have all the points, that single point in the middle there. So this becomes like a very different information geometry problem there. And I'm glad to report that we have some breakthrough recently about this. As I say, Dr. Hurley and I, we are able to show that this K-many rank space, which includes the ties, is a Hilbert space. That means it's a vector space and so on. Okay, and that is very exciting, very exciting. And you can see here, when we have a 3 there, n equal to 3, then n factorial is 6 points. But the K-many rank space with ties there, we have 13 points. But that number increases very highly, quickly. Because when we have a permutation of 5 elements, we have 120 n factorial. But then the K-many rank space there, we have 41 there. Good. Okay, so that's, I want to wrap up this. And, the next 3 pages are really the references there. Okay. Okay, so is there any questions?
Thank you, Professor Su. Thank you so much for your inspiring talk. Are there questions, comments from the audience? Please. Can you approach? And you too. Because the microphone is here.
Yeah.
Because the microphone is here.
Thank you. Thank you for your, can you hear me?
Yes. Yeah. I can hear you.
Interesting and inspiring talk. Ranking and the scoring, which you concentrate on. Sounds very interesting. Interesting across multiple disciplines, as you indicated.
That's right.
Let's consider two examples, two simple examples.
Yeah.
One is which you have already indicated, like Julia, just number of people to decide something about a parameter case. Okay, this is one example. The second example, do you consider a larger crowds for some ranking through social media? Let's say hundreds, thousands, could be million. Okay.
Yes.
I mean, do you see difference between these two kinds of cases? One is just a bunch of people, very small group of people, Julia like, and the other is crowd like. You know, there's a book called The Wisdom of Crowds, talking about the shared cognitive among the people, among the population, the crowds. The crowds, the idea is the average crowd is more smart than the few experts. So here, what I'm wondering is the scoring or ranking when applied to these two different cases. Do you see any difference, or do you any study on this kind of differences, if any? Thank you.
Yeah. Your question here is very, very important, very interesting question. You know, if we are talking about that data set items, D, capital D, right? And you're talking about, you know, in the recommended systems and so on. Now, capital D, you can have 100,000, right, of them, right? And then, but you know, if we go skating like that, it's very smaller. You know, the n equal to, you know, here the example I give you is n equal to 8 only, right? But now n equal to 8 or n equal to 100,000, right? Either way, the key is really that rank score function there. If we can calculate that rank score function, which is, you know, we converted the score to the rank for free, right? We do the sorting, and we know that, and everybody, you know, when we teach the courses there, the first thing about computational then is you got to do sorting, you got to do algorithm, you know, sorting there. Okay, so then if we have a score there, we convert the score function to a rank function, almost free in some sense. So we know that, you know, sorting algorithms, you know, can be, you know, the best one is n log n. You know, okay? And then once we converted that to the rank function there, then we can calculate the third function there, which I just showed that today, you know, on many PowerPoints here. It's called rank score function there. And, you know, the answer to your question is that once you calculate that rank score function and you draw the graphs there, okay, you draw the graphs between two models or two algorithms or two something, you name it, two approaches, and you compare those two rank score function graphs there, then you will know what's going on there, okay? And that's why I have that pictures of 3 rank score function there, you know, F sub A, F sub B, F sub C there. Okay, so anyway, I don't know if I answer your question a little bit or not, you know, that rank score function graphs, and then the difference between that rank score function graphs of A and a B, that would be the diversity, cognitive diversity there. That's the key, okay?
Yeah, thank you. I think you pointed the key issue, the diversity, which links to my talk before yesterday, talking about a mini, small, and a very few large. This diversity or opportunity probably is something which is yeah. Thank you very much. Thank you.
Yeah, and also I also want to point out that this rank score function is very similar to, in statistics, you call that cumulative distribution function. In statistics, what you do is that all the statistical approaches there, depending on, when you have a probability function there, then you calculate, you draw the probability distribution function, PDF there. So from the PDF there, we calculate CDF, cumulative distribution function there. But the point here is this, the very big difference here is that the CDF there, the x coordinate of CDF is the score. And the y coordinate of CDF is the probability. Yeah. So in the sense that's equivalent to the rank in some sense. Now, the point here is that if you have a function there, and depending on the score there, then your function there is really data item dependent. Okay? And that's why here, the rank score function, I dare to tell everybody that the rank score function, because it is from the rank to score, and therefore I can declare that. I'm very proudly to declare that. The rank score function or its cognitive diversity is data item independent. Okay? And that's why it's domain independent. It can be cut across any other domains.
Thank you. Very interesting. Particularly the respect to CDF, PDF, linked to this larger data set about the long tail or heavy tail distribution. Yeah. Thank you. I will continue a conversation. Maybe I'll send the email to your back. Thank you.
Yeah, please do that. Yeah, please. I'd like to have more conversation on that. Yeah.
Thank you.
Yeah.
Please.
Any questions?
Hello, yes. Thank you for the opportunity. It is indeed very, very interesting topic you explained.
Yeah.
So maybe my question is a bit, a very simple one, but I believe it's very, very important for everyone who is working with AI, with deep learning, especially. So when you are talking and developing about multi-layer combinatorial fashion, it includes model fashion of multiple machine learning or AI models.
That's
and
right.
also reinforcement learning.
Yeah.
So I'm wondering, how do you come up with determining the hyperparameters? It's a simple, but sometimes when your system is becoming complex and more complex, so determining the hyperparameters is not that easy. And when you are combining some AI models, do you use the same hyperparameters or do you use the different hyperparameters? For example, the hyperparameters that I mean is the number of layer, for example, the number of nodes in specific layers, the number of the value of learning rate. So that's very simple. But yeah, usually we are going to tune the parameters, but it takes very long time. Now I'm having the opportunity to ask with the expert, so I would like to hear the answer from the expert. Maybe.
Okay. Yeah. No, this is very, very also interesting and very, very important issues and also questions here you have. The way we can see the ranking. As I say, I originally said that the reason many machine learning, and if you look at machine learning books and AI books and so on, many of them don't talk about ranking. Okay, and one of the reasons again is that there are two reasons. Reason number one is that we don't know much about the structure, the infrastructure of the ranking space. Okay, we only know, we're familiar with the Euclidean space there, because in the Euclidean space there, you can do many things. Triangle inequality and other things there, and that's why you can see that all the CNN convolutional neural network and everything there is done on Euclidean space there. Okay. Now, the second reason people don't get into ranking that much is that it's a tie rankings there, because if you combine two rankings, combine two scoring there, you can get a tie ranking there. Okay, and people don't know how to get rid, how to take away. So the way to do that is that by using that Kameni, we have at the end I talk about Kameni rank space. Okay, and the Kameni in the 1959, he wrote a paper, very interesting fundamental paper, talking about mathematics without numbers. Okay, so he laid out that kind of time rankings and possibilities. Remember that in that hexagon there, and then you have 6 other points on the edges, and then you have 1 more point in the middle there. So if you have a time rankings of the 3 elements there, A, B, C, A, C, B, and da da da. If we include the time rankings there, we have 13 points there, rather than 6 points. Okay, so coming back to that is that what I do here is I do the multi-layer, okay, combinatorial fusion on the Kameni rank space there, and also do the deep learning there. Okay, so you can do it this way. Let me explain to you. Very interesting there. Your questions is very, very fundamental there. Here is that the way we do it here is that you have a machine learning. Right now you have a machine learning, AI, you have a data mining, you have all those things. Okay, so when you are given a problem, doesn't matter this problem is a big one or the big data or a small one or something like that, or cognitive neuroscience there. It doesn't have to be that big, but it's very cognitively, quite interesting. So what we do here is I say, okay, good. You extract out the features there or the attributes there. Then you can use the machine learning or AI or data mining techniques, to do the feature selection and the combination there. And then they say, okay, well, you got a 4 or 5 models, or machine learning models, or AI models, or data mining models, 4 or 5 of them, and you come out with result there, which is very good, but not good enough. Let's say you get a precision, maybe like a 75%. But that's not good enough. This is very good already. Good. Very good means that it's better than half a chance, 0.5. Okay, then after that we use combinatorial fusion. We ported that to the rank space, to the Kameni rank space there. So now imagine that in the Kameni rank space there, you take the 4 points there, 4 ranking there, and that ranking can be time rankings also. And then you try to combine those 4 of them. So what I did here in one of the examples there is that reference, I think number 15. We do it is that we have 4 models. We expand it to, with the rank combination, score combination, with average combination, weighted combination by performance, weighted combination by diversity strengths. We can expand that to, let's say, 66 models. Then we can reduce that to 4 models again. And then we can expand again, and we can reduce it again. And that's how we do a deep learning on the Kameni rank space. Okay.
Yeah.
Does that answer some of your questions?
Yeah. That's already answered my question.
And this is very, very interesting. If you want to know, please send me email. Yeah, I would like to talk to you more about this. Okay.
Yeah, I would like to.
Yeah.
If I have another question, so yeah.
Yeah, and this is whatever you want to do, deep learning. You want to do many things. Big data or whatever you want to do. You have 100,000 data set items. Fine, we can do that. Okay.
Yeah.
Thank you.
Thank you so much.
Yeah, sure. Thank you. Yeah.
Please come. Another question, Professor.
Yeah, sure.
Right, thanks, Professor Su, for the presentation. I also found the part on cognitive diversity very interesting.
Yeah.
I might be wrong, but I presume that the basis is the assumption that the procedure for judging and ranking is quite subjective. And I was wondering what happens if the process is a mixture of subjectivity and objectivity. For example, when the doctors assess a certain type of disease using questionnaires, it might be based on a set of questions. So this is the objectivity. But at the same time, it depends on who designed the questions and how these questions were designed. So this is the subjectivity. So I guess in these scenarios, let's say if we have method A, B, C, D to examine a certain type of disease, and this will give different rankings or scorings or to indicate how severe the disease is, or if there is the presence of disease. So I guess the question is, would this method still apply, or does it face with some challenges?
Yes. Yeah. This is very, very also interesting, important questions here. When we are, this subjectivity and objectivity is also play a very important role here. And we can see that even in machine learning, data mining, AI, and so on, I would say that all the models are very, we would say that, they all say they are very, objective, but I think that most of them are really subjective, right? Don't you agree? In some sense, right? We always say that, everybody, this is that nobody knows everything, but everybody knows something. You see?
Yeah, definitely.
So that's why if you apply a model, that if you apply regression, then regression, you're talking about really statistical way of doing things there. If you apply, say, okay, ensemble method, then you have all kinds of ensemble methods there. You are also very, very subjective. Okay, good. That's what I call the subjective means. What I mean is that, well, a model is designed by an algorithm or a person, right, and so on. So either an algorithm or a person. That's why we have this something called rank score function here. And so you can see that the rank score function is to characterize the ranking behavior or the scoring behavior of the algorithm or the model. Okay? And then we evaluate the cognitive diversity between those two models, and then to calculate that between those two models by calculating the difference between those two rank score functions. Yeah, right? Good. Now, so we do that. We do that combination on the rank community ranks there. Now, you can ask me another question. You say, well, Frank,
Yes. Yeah,
do
just
we,
add.
yeah.
I
Okay.
completely agree. And I was also wondering if the knowledge learned from a certain problem can be translated to a different scenario.
Yeah.
For example, the example you gave is the skating, judging, and scoring, right?
Yeah.
And let's say if it comes to horse riding or a completely different problem, the same knowledge still holds, or can it transfer somehow?
Well, yes, definitely, yes. Because in one of the 5 examples I gave it, in this PowerPoint, is about corporate revenue prediction there, right? So that's a very typical, traditional revenue prediction. But we can translate that into, 4 or 5 systems, and then how to combine them, by using computational fusion there. Okay, does that convince you? Yeah.
Cool. Yeah. Thanks very much.
Yeah. Let me also ask you a question. Yeah, sorry, I asked a question here. See, when we say that, right? Nobody knows everything. Okay, and everybody knows something, right?
Yeah.
So that comes that when we want to combine the model or the algorithm there together there. One of the questions very interesting here is also how many we should combine. Okay, how many models or how many algorithms we should combine. This is also a very, very subjective way of thinking. Okay. So the point here is that, over and over and over again, people, in different fields, machine learning, AI, data mining, statistical learning and you know, and you name it, computational learning, you know, computational science as well. The way, the number of models or algorithms we have combined got to be greater than 3.7. Yeah. Okay, does that make some sense? Yeah.
Yeah.
That means you cannot just combine two of them, because you combine two of them, you don't get the whole thing. You don't get, you know. But over and over, people show that by example that combination of that of the n models, when that n models become very, very good, sharply decrease the error rate at the point of n is roughly equal to 3.7. Okay, does that make sense now? That's why you want to form a committee now. You don't want to have this committee of 2 people. Okay, that's not good enough. You don't want to have a committee of 3 people. That's not good enough. You got to have a committee of at least 4 people. Otherwise, it's not a committee. Because otherwise, no matter how you do it, you don't get the whole thing. You don't try to get the whole thing. Anyways, there are many, many, many studies about that. 3.7 is a critical point there.
Okay. Thank you.
Yeah, sure.
Other questions? Okay. Thanks, Professor Su,
Okay.
for your very, very nice and inspiring talk.
Okay.
Thanks again.
Yeah, it's my pleasure. Yeah, thank you all. Yeah, again, you know, feel free to write me emails. Okay.
Okay. Thank you.
Okay. Bye.
Bye.
Yes, sir.